Hi guys, thanks for watching. This video is about Taylor series and it builds upon my video that was talking about general power series. So the first thing I should probably reiterate is what we had just finished on the previous video, which is basically how to construct a power series that approximates the arctangent of x. It involved term-by-term integration of a geometric series, and what we ended up with was this really cool equality that said the arctangent of x is equal to the infinite series that sums from 0 to infinity of -1 to the n times x plus 2n plus 1 over 2n plus 1. So basically, if you wanted to work with the arctangent of x and you were trying to plug in a value of x for which you didn't really know how to deal with the arctangent, you could use this infinite series on the left-hand side of this expression to figure out that value. So what I was talking about was trying to find, say, the arctangent of 0.17. What you would do is you would go over to this power series, plug 0.17 in for x, and then you would take a reasonably large number of terms from this infinite series. You'd basically truncate the series at some large power of x, and that would give you a pretty darn good approximation of the arctangent of x, as long as your x value is on that interval of convergence from -1 to 1. Now it turns out arctangent of x is not some special function where it's the only function that has a power series with this property. There's actually other functions that will have power series that we're going to memorize or learn about in this class to approximate that function. For example, f of x equals e to the x. That might be a really good function to have a power series for to approximate our function. Just think about it. If you're trying to figure out f of 0.34 without a calculator, how the heck would you figure out what e to the 0.34 is? That's not necessarily an easy question. You could figure out approximately how large that is, but finding a pretty precise value would be hard to do. We could actually use a cool trick using derivatives to construct a power series for f of x equals e to the x. So basically what we're saying is that we think e to the x should have a power series that approximates it. So let's use some derivatives to try to find out what it is. So first of all, let's suppose that e to the x does have a power series. So f of x equals e to the x equals c naught plus c1 times x plus c2 times x squared plus dot dot dot, where c1 and c2 and c3 are some constants, and and so on and so forth. We just don't know yet what those constants are. Well, one thing I could figure out is what c naught is, right? Like I should be able to plug in f of 0, and that's e to the 0, which is c naught. So c naught is e to the 0, which is 1. So I was able to knock out this very first term of that power series and figure out that it should equal the number 1. Well, if I take the derivative of this series, I should be able to figure out what c1 is. Let me show you how that'll work. So f prime of x is still e to the x, the special thing here being that e to the x is its own derivative. So f prime of x is e to the x, and then if I do term by term differentiation from this power series, the derivative with respect to x of c1x is c1. The derivative of c2x squared with respect to x is 2c2x. The derivative with respect to x of c3 x to the third is 3c3x squared, and so on and so forth. Well, I can apply this same trick over again. I could find out what f prime of 0 is, which should be e to the 0. So c1 ends up equaling 1. Alright, well I've got c naught is 1 and I've got c1 is 1. That doesn't mean that all of these coefficients are going to end up being 1 though. You'll see what starts to happen. So f double prime of x is still e to the x. E to the x has its second and third and fourth and fifth derivatives, etc., still being e to the x. And I'll do term by term differentiation again. So d dx of 2c2x is 2c2. d dx of 3c3x squared is 6c3x, and so on and so forth. You can continue on in that fashion. And now we're going to find out what the second derivative of f is, evaluated at 0. Well, that's e to the 0 equals 2c2. So now I have a little equation to solve. solve this for C2 and you get 1/2. E to the 0 over 2 is 1 over 2, which is 1/2. And anyway, you could start to see some patterns, and you could see how this is going to continue. So we could do the third derivative, and there it is. There's our third derivative, and you end up getting that C3 is 1/6. And you could do this for the fourth derivative as well, and you're going to end up getting that C4 ends up equaling 1/24. And now, one thing you might want to do, and you're under no obligation to do this, but I think a good idea would be to pause the video right now and see if you could find a pattern with C0 being 1 over 1, C1 being 1 over 1, C2 being 1 over 2, C3 being 1/6, C4 being 1/24. And you will eventually figure out what that pattern is, so I'll let you pause it now and restart it. Okay, now that you're back, or maybe you didn't pause the video in the first place, but either way, what you probably are starting to see is a good formula for C sub n, the nth coefficient in this power series, is 1 over n factorial. You can see C0 being 1 over 1, that's the same thing as 1 over 0 factorial. Remember, 0 factorial is equal to 1. Or C1 is 1 over 1 factorial, C2 is 1 over 2 factorial, C3 is actually 1 over 3 factorial, and C4 is 1 over 4 factorial. So that's a great formula for this. So there it is, all lined up in a nice little table. And what we have is a really convenient power series describing e to the x. So our C sub n is 1 over n factorial, and e to the x, by the way, you're going to want to memorize this, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so forth, out to infinity. And in summation notation, in sigma notation, that's the sum from n equals 0 to infinity of x to the n over n factorial. That's a really convenient formula for figuring out how e to the x should behave. This is called a Taylor series for e to the x centered at x equals 0. We call it a Taylor series instead of a power series because a Taylor series is a specific kind of power series that you find using derivatives in this way. It's got infinitely many terms, and basically what we have is e to the x is approximately equal to, well, a not so bad approximation for e to the x near x equals 0 is actually just the constant line y equals 1. Now that's only good very near x equals 0. An even better approximation is e to the x is pretty close to 1 plus x. We could do even better than that. E to the x looks pretty close to 1 plus x squared over 2 factorial near the origin, near x equals 0, near where it's centered. What these are called are partial sums of the Taylor series. So let's try to think like a computer or like a calculator for a second. Let's say that the user plugs in a function f of x equals e to the x, and the user wants to know what f of 0.153 is equal to. Like I said in my previous video, the calculator does not have a magical list of every input-output combination for e to the x. It doesn't have a table where it knows that e to the 0.153 is equal to whatever value it's equal to. Instead, what the calculator does is it takes a reasonably big partial sum of this Taylor Taylor series. It's called a Taylor polynomial. Let's say maybe it has the degree 5 Taylor polynomial stored in there. And so what it does is instead of computing e to the 0.153, what it does is it goes to this Taylor polynomial and it plugs 0.153 in for each of these x values. And that's a reasonably good approximation for e to the 0.153. If you need a better approximation, you take more powers of x. And as n tends to infinity, as the number of terms tends to infinity, then we eventually get this equality that we have up at the top. that e to the x is actually equal to the infinite sum from 0 to infinity of x to the n over n factorial. Of course, an infinite sum is not really something we can work with ourselves because we can't type an infinite number of terms into our calculator. Now you could see this in action if you go to Desmos. So we'll go to f of x, and we could put in e to the x. Let's see if it'll graph it. For some reason it's not happy with e to the x. Let's try exp of x. Well, it's not happy with it right now. Oh, I probably have to zoom back out. That's going to be the problem. There it is. There's f of x equals e to the x. If you ever try typing in e to the x into a computer or a calculator and it doesn't work, exp of x is usually the calculator syntax for making that work. So that's why I tried exp of x. And then let's try g of x, which is going to be equal to the sum from n equals 0 up to, we can't put in infinity, so put in a reasonably large number, let's say 25, of, it's going to be x to the n over n factorial. And we better get these colors here so that we can see the difference between the two graphs. It turns out that the picture that I generated is so good on this window you can't even tell the difference between the two graphs. If I zoom out far enough though, you could see that they start to veer off. You could see y equals e to the x going along the y-axis or the x-axis here, and then suddenly starting to follow this polynomial. Now we could change this largest power of x here. Let's make it a lot smaller. Let's just make it the sum from 0 to 4 of x to the n over n factorial. And this is a little bit easier to see what's going on. We could see that we have y equals e to the x in blue, and then we have a degree 4 polynomial in red. And for a little while, it seems like they overlap pretty good, and then they start to veer off as we get away from x equals 0, as we get away from the center. And as these powers of x get larger, so 5, then 6, then 7, you can see these approximations are getting better and better and better. And I can actually keep going until they're going to overlap so well that on the window range that I'm in, you can't even tell that they differ at all. So here's 20, here's 30. They almost overlap perfectly except for down here. Let's try 35. And now they look like they overlap perfectly. Of course, if you zoom out, you're going to see that they don't overlap perfectly. They just overlapped perfectly on that window I was on. To get the red and the blue graphs to overlap exactly, we'd have to be able to plug in an infinity into the sum, which is not something that's computationally possible. Okay, so continuing on. So we've seen this slide already. These are called Taylor polynomials. Truncating a Taylor series to a finite highest power of x is called a Taylor polynomial. Right now we're at the Taylor polynomial of degree 5. Now this is the Taylor polynomial of degree 6, the Taylor polynomial of degree 7, and so on and so forth. And actually here's another representation of it. So e to the x equals an infinite sum of polynomial terms, but we could say that e to the x is reasonably approximated by y equals 1 near the origin here. And then it's better with 1 plus x, and then even better with 1 plus x squared over 2 factorial. And it's the same thing I was just showing you in Desmos. It gets better and better as we go. But the only way to get it to overlap perfectly is not to use a Taylor polynomial that's truncated, but to use a Taylor series that goes on forever, which is not something you could actually type into a calculator. Okay, so let's see what it's used for. Use a degree 3 Taylor polynomial for f of x equals e to the x to approximate f of 1, which is equal to e. So basically, we could use a Taylor polynomial to get a pretty good idea of what the decimal expansion of the number e is. I know that you all know that it's 2.71 something, but we can use Taylor polynomials to get an arbitrarily accurate approximation of the number e. So let's say f of x is equal to e to the x, which is approximately equal to its degree 3 Taylor polynomial, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. You could see that they overlap pretty well, not perfectly, but pretty well on our interval. And so if we're trying to approximate e to the first, or f of 1, you can see those two graphs are pretty close. They're not perfectly overlapping, but they're close enough that we can get a reasonable approximation of what the decimal expansion of e is, which is probably the first time in our mathematical career that we could do so. As I zoom in further, you get a better idea of how it's a good approximation, but it's not perfect. A degree 3 Taylor polynomial is not going to be perfect. It's going to do a pretty good job, but it's not going to be exactly right. So what I'm going to do is I'm going to evaluate that polynomial at x equals 1. Notice how I'm saying f of 1 is approximately equal to this degree 3 polynomial evaluated at x equals 1. It's not a perfect equality, it's an approximation, but it's a reasonably good approximation. I get 2.6 repeating. It's not exactly 2.71, but you know, I'm in a pretty good ballpark. And if I go to a degree 4 Taylor polynomial or a degree 5 Taylor polynomial, in a very short amount of time, I'm going to get such a good approximation for the decimal expansion of e that the error is hidden in terms I'm not even looking at. Maybe the error doesn't start until the 100th decimal place of the decimal expansion, in which case I'm probably not even looking for that. That's beyond my margin for error that I need to worry about. We can figure out, by the way, how accurate our estimate of 2.6 repeating is. It doesn't look perfect, but if we do actual minus estimate over actual, we could see that in just a couple seconds of calculation, we were able to calculate the decimal expansion for e within a 2% margin for error, which is incredibly good, right? Plugging into a degree 3 polynomial, and I was able to approximate e with in less than 2% error, with less than 2% error. Now it turns out that this is a general idea. It does not just apply to e to the x. We could generate Taylor series for all sorts of functions. So as long as f is an infinitely differentiable function on an open interval, so basically as long as you have a function that you can keep taking derivatives of, because remember the Taylor series was found using derivatives, and if we're centering our Taylor series at x equals a, then the Taylor series generated by f at x equals a is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a quantity squared. This is a formula you're going to have to memorize, but it turns out that each term is not too hard to remember, particularly if you notice that each term is really just, you look at what position it's in the sum. So this first term corresponds with n equals 0. That's basically the 0th derivative of f at a, so you can think of that as the 0th derivative, times x minus a to the 0 over 0 factorial. The second term is when n is equal to 1. Well, it's the first derivative of f at a times x minus a to the first power over 1 factorial, and that continues for all of these terms. So you just figure out for each individual term where it is in the sum, and you plug into the formula from there. And then we define the degree n Taylor polynomial, not Taylor series, but Taylor polynomial, as basically a truncation of the infinite Taylor series. So the degree n Taylor polynomial is taking terms up to the degree n term, and then you truncate there. In the real world, the Taylor polynomials are what we use to approximate functions that are hard to work with, because we can't plug into an infinite series, but a Taylor polynomial of some degree that's manageable, that's something we can work with. By the way, you're going to see this in your textbook, and you'll see this in your Math Excel homework. The term Maclaurin series, if you see that thrown around, a Maclaurin series is just the Taylor series centered at a equals 0 or at x equals 0. So a Taylor series centered at the origin is called a Maclaurin series. I kind of think we should call all of these Taylor series just to keep it simple, but I don't really make the rules. So if you see someone mentioning a Maclaurin series, what they're talking about is a Taylor series where all of these a's are equal to 0. Okay, let's figure out a Taylor series for sine of x. So we should be able, and let's center it at x equals 0, by the way. So technically this is a Maclaurin series for sine of x because we're going to center it at x equals 0. So the first thing you do is you write out the formula that's on the previous slide. And that's a formula that you're going to have to memorize. But I kind of just showed you some tricks for remembering how to figure out each term in that sum. Okay, in any case, since we're going to have an a value of 0, since we're centered at x equals 0, that means a is equal to 0. So we have f of 0, f prime of 0, f double prime of 0, these x's. I'm just writing x instead of x minus a because each of these x's is actually an x minus 0. Okay, so what I'm going to do is find out the first few derivatives of the sine of x. So the 0th derivative of sine of x is just sine of x. The first derivative of sine of x is cosine of x. The second derivative of sine of x is negative sine of x, and so on and so forth. And then the rest of the table, so what I'm talking about right now is all these derivatives of sine of x. Then I'm plugging in 0 into each of those derivatives, and the 0th derivative of f of x evaluated at 0 is 0. The first derivative of sine of x evaluated at 0 is 0, and so on and so forth. I get all these. So the first derivative at 0 is 1. The second derivative at 0 is 0. Just plugging in 0 into these expressions and figuring out what I get. And then to figure out what the nth term in your Taylor series is, so this first term here, let me erase all this ink actually, it'll be easier to see. Erase all ink on slide. Okay, so the first term in our Taylor series is f of 0, so the nth term, that first term is just 0. Then I need to do f prime of 0 times x. Well, that's 1 times x. So 1 times x is just x. Now for the degree 2 term, since this coefficient is 0, we know we have 0 there. And now let's take a look at the degree 3 term. That should be, let's see, this should be the third derivative of sine of x evaluated at 0 times x minus 0 to the third, or just x to the third, over 3 factorial. So I have negative 1 times x to the third over 3 factorial, or just negative x to the third over 3 factorial. And I continue on in that fashion. The degree 4 term is 0, so I left it out. The degree 5 term is x to the 5th over 5 factorial, and so on and so forth. So now what I have, look up at the top of the screen here, I have the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and it continues on in that fashion. The powers keep going up by multiples of by 2 each time, so by odd numbers. The signs keep alternating. The denominator keeps going up by a factorial of an odd number. And so the sigma notation is the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. So now I have a Taylor series for sine of x. This is another Taylor series you're going to have to memorize. E to the x is one you have to memorize. Sine of x is one that you're going to have to memorize. There's going to be a whole bunch to memorize, kind of like the top 20 integral sheet that you had from the beginning of the school year. But what we won't do is derive the Taylor series for every single function you're going to be memorizing, because that would just take forever. But every Taylor series you are going to memorize is going to be something that you could derive in the way that I just showed you. Now a cool thing is this Taylor series converges for all real numbers. Same thing with the e to the x Taylor series we were looking at. It converges for all real numbers. So no matter what power or what number you put in for x, as long as you take enough powers in your Taylor series, as long as you take a Taylor polynomial that's got a large enough degree, it'll be a pretty good approximation of sine of x. So here, let me show you. We could get this graphical. So the degree 1 Taylor polynomial for sine of x is x. So you could see near the origin, the sine of x is approximately equal to x. If I want to do better than that, I could take the degree 3 Taylor polynomial, and sine of x is pretty close to that near the origin. It's a good approximation. It's exactly equal at the center, and then it slowly starts to veer off from there. The degree 5 Taylor polynomial, it's exactly equal at the center of x equals 0, and it's a better approximation, but it still does veer off eventually. As we take larger and larger Taylor polynomials, larger and larger degree Taylor polynomials, it gets better and better and better. I could eventually get it to the point that in the window range I'm in, the graphs overlap so perfectly that you can barely tell that they're different from each other. Of course, if I were able to zoom out this graph, you would see that it still doesn't overlap perfectly. The only way to get them to overlap perfectly is to have an infinite series, an infinite number of powers, which is not computationally possible. And once again, this is something you could try out in Desmos. You can go into Desmos, and they've actually got a built-in demo that you could try out. So you click this, this upper left-hand corner, and they've got some graphs that are already pre-generated for you. Go down to Calculus, which is near the bottom, and you can see Taylor expansion of sine of x, an open graph. And they've even put in a slider for you where you could figure out what degree Taylor polynomial you want to do. So this is the degree, let's see, the degree 3 Taylor polynomial. It'll let you go up all the way to the degree 21 Taylor polynomial. Now, I'm getting the number 21 by doing 2 times 10 plus 1 to get 21, so the degree 21 Taylor polynomial. And you can see it overlaps pretty darn well with the sine graph, but if you zoom out, it's still not perfect. The only way to make it perfect is to have an infinite number of powers of x, which is not something you could actually do. Okay, and let's do 2 quick examples that'll help you on your homework, and then we'll be done. So example 4, let f be an infinitely differentiable function for all real numbers. Assume f of 1 is 2, f prime of 1 is 1, f double prime of 1 is -2, and f triple prime of 1 is -3. And it says write the third order Taylor polynomial for f at x equals 1, and you use it to approximate f of 1.2. Alright, so all we're going to do is we're going to take the formula that we've already looked at on the previous slide, and I'm plugging in 1 for a, because my Taylor polynomial is going to be, or my Taylor series is going to be centered at x equals, or a equals 1. So I'm plugging in all those 1s where I had a's. And I'm truncating my Taylor series at degree 3, because I want to use a degree 3 Taylor polynomial, or third order Taylor polynomial, to approximate f of 1.2. Now they gave me all those derivatives. I know what f of 1 is. It's 2, they gave it to me. I know what f prime of 1 is. They gave it to me, it's 1. And so on and so forth, right? I know that the second derivative of f at 1 was given to me to be -2, and the third derivative at 1 was given to me as -3. And now, just simplify a little bit just to make it a little bit easier to work with. That's just the degree 3 polynomial that we can use to approximate f of 1.2. So let's do it. F of 1.2 is not equal to, but is approximately equal to 2.156, which I found by replacing all of the x's with 1.2's. Now here's the amazing thing about this example. Here's what makes this cool. We were able to figure out information about the behavior of a function f only by knowing what its derivatives was doing, right? Or what its derivatives were doing. I don't have an equation for f. I don't know that f is the sine of x, or f of x is the cosine of x, or f of x is 1 plus x cubed all over x squared. I have no information of that kind. All I know is that I've got some function f and that its derivatives are equal to a couple different values at x equals 1. But I was able to use those couple values of the derivative to approximate what the function itself was doing. So in many ways, you could think of a Taylor series as a way of figuring out how a function is going to behave based on how its derivatives behave, which is kind of an amazing thing. And let's just do one more quick example because it helps on the homework. Find the Taylor polynomial of order 3 generated by this new function f at x equals -1. So f of x is given to us as x cubed plus x minus 3. And we're going to find the degree 3 Taylor polynomial that's generated by f centered at x equals -1. So take the formula that was on the previous slides, plug in a being a value of -1, which you can see right here, all the places where a shows up in the formula, I'm putting in -1. I'm truncating at degree 3 because it says use a Taylor polynomial of order 3 or of degree 3. And I'm going to find out what f of x and its derivatives are. So f of x is x cubed plus x minus 3. F prime of x is 3x squared plus 1. F double prime of x is 6x. And f triple prime of x is 6. I'm just taking a sequence of derivatives here. Just do d dx each time to go from one derivative to the next. And then I'll plug in x equals -1 into each of those. And I get -5, 4, -6, and 6. Plug those into the formula and you're done. The degree 3 Taylor polynomial for f of x equals x cubed plus x minus 3 is this guy right here. Now remember how the AP test works. You don't have to simplify your expressions on the free response portion of the test to get credit. So this would be a perfectly acceptable final answer on the free response portion of the AP test. Of course, on multiple choice, sometimes multiple choice questions will be simplified, so you might have to simplify for a multiple choice question. And on your Math Excel homework, very likely that they're going to have you simplify for that as well. So there's your final answer. Alright guys, I hope this video was helpful, and please let me know if you have any questions, and I hope you enjoy your day off. Bye-bye.